climate change is one symptom, but just one symptom only, of a much greater problem of human ecological dysfunction. The human system, the whole of the human enterprise, has already exceeded the carrying capacity of the planet for human beings. The work we do is in terms of something we call ecological footprint analysis. Ecological footprinting attempts to identify, to quantify the total area of ecosystems required by any specified population to produce all of its resources and to assimilate its important wastes. And what we have found is that the total human eco-footprint already exceeds the biocapacity of the planet. Carbon dioxide, one of the principal drivers of climate change, is the single largest waste output in all industrial economies. So we have a dilemma. The dilemma is this: we're already in excess of the global capacity to assimilate carbon dioxide, and yet 3 billion people live in more or less poverty. This means we can't possibly hope to raise those people to a decent standard of living using any existing technologies without completely destroying the capacity of the Earth system to sustain human beings. We need carbon taxes. We need cap, auction, and trade systems in place so that the price of fossil fuel tells the truth about the ecological damage costs of its use. And until that happens, this problem will not be solved. We need a global scheme in which the rights of access to the world's carbon assimilation capacity is allocated to countries on a per capita basis. Each human life is equivalent to every other human life. And that would mean that countries like Canada or the United States, which use 4 or 5 times as much fossil fuel as the average person, would be stuck with only the rights of a person in a very poor country who is underutilizing his or her access to the atmosphere. So that means we would set up the basis for a global trade in carbon rights. In other words, let's cap the emissions of carbon dioxide at the level that is assimilatable by the atmosphere. Allocate the remaining capacity equally to people around the world. Countries that are underutilizing their capacity would have excess rights. Countries like Canada, the United States, Europe that are overutilizing their fair share would have to buy those rights from other countries. So we'd have a global system of cap and trade in carbon rights based on the fundamental rights of individuals being equitable. We can no longer operate as individuals or even as individual countries. It's not possible for any single person or any single city or any single country to become sustainable on its own. We're all on the same ship. The ship will either sink with all of us or float with all of us. This is a collective problem requiring collective solutions, and that means that we come together as a global community, forget the politics, in order to conserve life on Earth, or at least the prospects for civilized human existence. We need a global strategy in which we must reduce our carbon emissions and other greenhouse gas emissions by 80% before the middle to end of this century. My primary message was that people stop being either optimistic or pessimistic, simply get realistic about the nature of our situation, and start acting as if the science meant something. You know, humans claim to be a species of high intelligence, capable of logical analysis. We claim to be capable of forward planning. I teach in a planning school. The assumption is that we can take available information and plan for a better future. We claim to be a species capable of making moral judgments. So there are 3 qualities that make us human and raise us above all the other life forms on the planet. And yet, when you think of it in the collective sense, there's no evidence that the world as a community at any of the climate summits so far has applied collective intelligence to these problems. We are not planning as if we have a stake in the future, and we're certainly not extending our moral judgment to recognize that it's simply morally and ethically inappropriate for the rich to continue to consume 4 or 5 times their fair share of the world's fossil fuel resources and to use 4 or 5 times their fair share per capita of the world's assimilation capacity. So my message is get human, be intelligent, plan for the future, and exercise your moral judgment. And if we do those three things on a collective level, this problem will be solved.
What field of science do you work in, and how long have you been doing it for?
I'm a climatologist, and I've been working on climate change related issues. I've been working on this field for about 20 years.
Did your recent report, Human-Induced Arctic Moistening, yield any interesting findings or results?
Okay, that report itself is very interesting in that we were first to demonstrate that human activity has actually contributed to the increase of precipitation in the northern high latitude. This is a kind of things that we have been expecting from climate model simulations or from climate model studies, and from theoretical expectation or from understanding of how moisture, how atmosphere will react to the increase in temperature. And it was also what we see in the observations, or amount of precipitation measured in different parts of northern high latitude. But we were the first actually piece together between what we see in observations, what was the expectation in the theoretical work or the model simulations.
What's a climate change indices, and how's it used? And also, what's your involvement in developing it?
Well, climate is a fairly complicated thing. It is not something that we can put a lab that we can experiment on. And it is so complicated that we even don't have a complete observation covers every aspect of climate. So, but still we need to study it. The indices are the kind of things that we develop such that with this kind of indices we can measure, we can quantify different kind of aspects of changes in climate. That is, if you want to know how tall is some person, you need to have a meter or you need to have a tape. So this kind of indices are different kind of metric that we use to quantify different aspects of changes in the climate. We helped the World Meteorological Organization to develop a suite of indicators that can be used to quantify changes in extreme weather and climate. And this set of indices has been used in all countries. So what we try to do is we help different countries, especially relatively poorer countries, where they have smaller capacity in doing their own research. We help them to use our indices such that when they do their analysis, then their analysis can be matched or can be pieced together with people doing similar analysis using our method indices in different parts of the world. So essentially it's somebody draw a map for China, somebody draw a map for India. When we have both India and China work together, we get a map that actually matches around the border. That's the kind of thing we try to do. So by doing that, we can have a global coverage. That's why we can see changes of this kind of extremes in different parts of the world. Okay.
If you had the attention of the delegates at the upcoming United Nations Framework Convention on Climate Change in South Africa, what would you like to share with them about your current research?
Well, there are a couple of things that I think everybody needs to really understand. One is climate change is real, and that is mainly caused by anthropogenic influence. For that reason, we need to do two things. One is that we have to try to find a way to mitigate such that we reduce our human emissions of greenhouse gases to the atmosphere. However, this is not good enough because anything that we do now will only have impact for much longer term, which means that it's not immediate because we have already put too much greenhouse gases into the atmosphere. The warming will be there for many years, for thousands of years. Therefore, it is very urgent for everybody to think about how to adapt to the changes in the climate. So you really need to think about what you can do in order to reduce the impact of climate change on you or on ecosystems. The third thing I think people need to understand is that we do need to have fairly good mechanism to exchange information and data, because that's a way that helps scientists to have a better understanding of what's going on and what might be the future climate. And that itself will help to make a more informed decision about adaptation to the changes in the climate.
I've looked a little bit at some effects of climate change, for example on forest fire. Well, we've seen an increase in area burnt by forest fire over Canada in response to warming, so we might expect that that trend will continue. The most obvious thing is that we expect the climate to continue to get warmer. If we stopped emitting greenhouse gases completely today, the climate would stay approximately, the temperature would stay approximately constant, but we're not going to do that. We're bound to continue emitting some greenhouse gases, so we can certainly say that the climate is going to continue to get warmer. Of course, policy choices today will affect how much the climate warms, and like I already said, this will have implications for agriculture, for flooding. There's certainly potential for big impacts there.
ISIMOD, being a regional knowledge and learning center working in the 8 countries in the Hindu-Kush-Himalaya region, wants to improve understanding about mountain development and explore potential solutions to solve the challenges we are facing at the moment, like climate change, biodiversity crisis, globalization, and so on, and contribute to better livelihood of people living in the region. And it is equally important to safeguard mountain ecosystems, since goods and services offered by them are equally useful and are used by people living in downstream and to run several economic activities. To highlight this, during the Conference of Parties 70th meeting to UNFCCC in Durban, ISIMOD is organizing a series of activities that includes a meeting of Asian communities. We call it Meeting of Minds, where we are trying to discuss on how do we develop climate change adaptation measures in the region. And the most important event will be on 4th of December, Mountain Day. So this special day is dedicated to experts coming from different countries in the region and other parts of the world. We try to develop a global partnership mechanism to debate on mountain issues and explore the ways to highlight importance of mountain in the climate change debate. Talking about the most critical issue in the context of climate change in the mountain areas, I think water sector plays an important role. We can't really miss it, because water sector is critical when you talk about impacts and also climate change regulations. This is why we are emphasizing very important role played by mountains in the Hindu Kush Himalayas, which are also known as water towers of Asia. Unless we safeguard this precious and very important ecosystem, all other issues will remain unsustainable. It doesn't matter whether you are industrially developed or not. Unless you safeguard mountains, things will be badly affected. And we like to utilize the opportunity provided by COP17 to give a clear message to the global community about the significance of mountain ecosystems to regulate climate, preserve biodiversity, and offer numerous goods and services to people living in the mountains and downstream, and how mountain ecosystems are very much vulnerable to climate change impacts. At the end, what can be done to solve these problems through global mechanisms like UNFCCC negotiations and discussions. Thank you very much.
A senior researcher, Dr. Cohen focuses on regional assessments of climate change impacts and adaptation. In particular, he and his colleagues have recently been investigating the potential changes in snowpack on the North Shore Mountains overlooking Vancouver. This snowpack, which feeds our Metro Vancouver area reservoirs, could raise potentially troubling issues in the nearby future. Dr. Cohen attempts to address these issues, bridging the gap between climate change research and adaptation planning.
Hello, my name is Stuart Cohen, and I'm a researcher with Environment Canada, and I also work at the University of British Columbia. One of the things I do at the University of British Columbia is I teach a course on climate change called Climate Change in the 21st Century. I wrote a textbook with that title. It was published by McGill Queen's University Press. And the theme of the book is to discuss how to make connections between what climate scientists do to project future climate and what the concerns might be at a local level. How might a future climate affect watersheds, forests, food production, coastal zones, fisheries, and people? This concern is given the name climate impact assessment. So if there's going to be a warmer climate, what might the impacts be? And if we can understand what the impacts might be, how might we plan for this? How might we adapt to this? And one case that I'd like to illustrate for you is a case involving potential changes in snowpack on mountains that supply water to the city of Vancouver. So what we have here on the screen is the beginning of this story. We have a scenario, a potential projection of the future, in which in the Vancouver region, less of the precipitation that we would normally get in the mountains of Vancouver would fall as snow and more would fall as rain. The potential, therefore, is that the snowpack that we have in the spring might be reduced. And if we have a shorter snow season and an earlier snow melt, what might that look like? Well, here at the university, there is a group that actually does visualizations. And so I brought this visualization group together with some colleagues of mine from Environment Canada that had a snowmelt model and generated future snowpack. And what they produced was this graph showing how the elevation for snow on a typical April the 1st might change in a future climate change. This label here refers to a projection of future climate. The A2 refers to a very high emissions scenario. And this elevation here is elevation above sea level. So what you're seeing here is where, according to this snowmelt model, the snow line on April 1st of each year is going to be. And you can tell from this graph that it looks like the snow line is going to reach slightly higher elevations over the period of this model simulation. But suppose we could actually put this onto a three-dimensional graphic. And so the group here at the Visualization Lab here at UBC, led by Professor Stephen Shepard, was able to produce this three-dimensional image of Mount Seymour, which is in the district of North Vancouver, and they put on this white coloring, which shows where the snow line is on April the 1st. And right now, you're seeing an image of where the snow line is in the year 2000. If we advance this forward, you see that it moved up just a little bit, consistent with the change in the output of the snowmelt model. If we advance a little farther, now we're over here. See, it's slightly higher up now, and it shows that on the image. And finally, we'll go out to the end of this simulation, where the snow line is now at a much higher elevation, and so here it is. That's what it looks like from a side view. Professor Shepard's group also showed this from a top-down view. So this is the first picture of the current day, 2020s, 2050s, and 2100. So if we get a warmer climate, this is how the snowpack would visually change on this landscape. And what we hope to do with pictures like this is to help to make the connection between climate science projections, a physical impact that might occur on our landscape, and what that might mean for the management of that landscape. So in this case, we were speaking with the engineers and the water managers for Metro Vancouver and asked them, well, what's the best way to adapt to something like this? Because if we have less snow, that affects how reservoirs are managed. That affects how water is managed during the growing season. And so if we can make these connections between climate science, climate impacts, and adaptation, then hopefully science will be able to enable adaptation planning to occur, not just among engineers in Metro Vancouver, but anyone who's interested in water issues and similar issues around the world.
Why should people around the world be concerned about the changes that we're seeing in the Arctic?
Well, people around the world should be concerned about the changes because what's happening in the north is going to happen elsewhere. And because the north holds so much ice, and because that ice has the potential of melting and changing things like ocean currents and climate and raising sea levels, what's happening in the north is already worrying people in the south, in the tropics, because people who live at sea level are concerned that they're going to have to move. Well, I think the signs of hope are in the youth. You know, the kids that are on this trip on Students on Ice, they're learning a lot, they're becoming aware of a lot of things, and they're going to become activists. You know, in a group of 70-odd kids, you're going to find that this experience of being in the north is life-changing. For some of them, they're going to become activists, they're going to become biologists or oceanographers or who knows what, but all of them are going to be aware.
And what is the biggest threat to glaciers?
Definitely climate change. The warming of the atmosphere is melting the glaciers away, and it's significant. Glaciers provide fresh water for all of civilizations. The vast majority of people in the world rely on snow and ice melt that's emerging from the world's mountain systems and flowing down to the lower plain areas where people live. 85% of Greenland is covered in ice. It's the second largest ice body in the world. The area of melt, called the ablation zone, has doubled in size over the last 20 years. 16% more meltwater is being produced than it was 20 years ago.
And why does it matter that there's such a large chunk of ice here on Greenland as it disappears? Why does that matter to people who don't live here? Because only a very small population lives here, right?
Well, if we remove that ice off of the island of Greenland and transfer it into the oceans, oceans would rise in their levels by several tens of meters. That would flood out coastal cities. Florida would be underwater. Victoria would be underwater. It would just be catastrophic.
Right now we're in the North Atlantic on our way from Iceland to Greenland, and this is a really important place in terms of global oceanography because it's a place where North Atlantic deep water forms. So you must get really excited when you get to this part of the world, right? I'm pretty stoked to be here. Yeah, this is awesome. The polar regions are experiencing climate change faster than anywhere else on the planet. Everywhere in the Arctic and in the subpolar North Atlantic is warming quite quickly. So there's a lot of changes going on here. So many that it's actually hard to keep up with all of the changes. We can see changes in North Atlantic deep water. It seems to be becoming fresher. We don't really know exactly why, but there's a lot of change going on. The biggest change is in the sea ice. We've seen the sea ice retreat much faster than expected. We have a lot of computer models that had projected that sea ice would shrink as time goes on and as the climate warms. But it turns out that the observations, especially over the last 3 or 4 years, have been much worse than expected. We've seen dramatic losses of sea ice, and this is really changing the whole Arctic environment. The whole ocean is connected. If something happens in one place, it affects another place. But here in the North Atlantic, because it's so important for this global ocean circulation, it's a particularly important place to watch. The North Atlantic has a really critical role in terms of bringing oxygen down into the deep ocean, and also for helping to bring nutrients back up to the surface ocean where there's sunlight and where things can grow. As climate change warms the polar regions, ice sheets, like the Greenland ice sheet, are melting quickly, and this is supplying a lot of fresh water into the oceans. That fresh water makes the surface of oceans, like the surface of the North Atlantic here, less dense. And when the density decreases, these waters have a hard time getting down into the deep ocean. As the formation of North Atlantic deep water slows down because of the freshening, it reduces the supply of oxygen to the deep ocean here and everywhere else in the world.
Some of the worst impacts of climate change are going to be on water resources. And so we're already beginning to see the impacts of climate change on water resources around the world, but especially in California. We're seeing losses of snowpack in the Sierra Nevada mountains as the earth warms up. We're seeing changes in the timing of flow from those rivers that feed the delta as the snow melts earlier, as more rain, we get more rain and less snow in the winter. We're seeing more evaporation as the earth warms up and as the temperatures rise. Climate change is going to be a problem. Water managers are not prepared to deal with climate change, and yet it's a new challenge for water resources in California and around the world.
The effects of climate change is already been seen, and in particular when it comes to mass coral bleaching event due to increased sea surface temperatures, we've been seeing an increased incidence of bleaching events on reefs. We first started seeing mass bleaching in Belize and this region in 1995, and since then we've had bleaching in 1998, in 2005, 2008, 2009. So you can see the frequency and the time lapse between occurrence of these incidents are, the frequency is increasing and the time lapse is also, narrowing as well.
What would you say is the biggest threat to corals in the world today?
Well, you're right. One of the most fragile ecosystems in the planet against climate change is are coral reefs. And they have a built-in fragility. They are incredibly efficient in terms of harvesting light, and that in turn represents a very enormous fragility. Minute changes in temperature can produce very large events in the community. So at a global scale, I guess climate change would be my first choice for the global threat.
And can you explain a bit about the specific ways that climate change affects corals? Because there are a number of ways, right?
Well, yes, the most obvious one, and the most dramatic one, I would say also, is a phenomenon known as coral bleaching. So the color of the corals is due in a large part by the presence of millions of minute microalgae in the tissue of the coral. And these microalgae are very important for the nutrition of the coral. Most of the nutrition of a coral comes from these tiny little microalgae. So when corals are exposed to temperatures as, let's say, 1.5 degrees above the summer average, there's a mass expulsion of this algae, and you can see the skeleton, the white skeleton of a coral through the transparent tissue. And we call that phenomenon coral bleaching. And depending on the intensity of coral bleaching, it can lead to mass mortality of corals. It's a threat because it doesn't provide the conditions for corals to grow and to form this three-dimensional structure that represents the habitat for, let's say, 25% of the species of fish in the planet.
Two of the pieces of work that we've been doing lately concern abrupt climate change. This is a kind of climate change where the whole climate system changes over a very large scale, and it's hard for the climate system to go back to the way it was before. And two of the types of abrupt climate change we've been investigating are changes in the big land ice sheets, Greenland and Antarctica, and also in deposits of methane on the ocean floor known as clathrates. And the discoveries that we've made in those areas suggest that abrupt climate change, due to major changes in land ice and due to release of methane from clathrates may be much more severe than previously thought. So climate change is caused, of course, by emissions from humankind. Probably the biggest crisis is that we continue to emit carbon dioxide at a very rapid clip. And measures to try to slow down the rate of carbon dioxide emission really have not taken hold internationally. Our best understanding is that the emission of carbon dioxide by humankind is the primary driver for climate change. And in some sense, the biggest crisis that we face is that internationally, we have not started really coherent collective action by the whole of humanity to slow down those emissions. In terms of the effects of climate change, there are increasing signs that extreme climate change, this means short, rapid changes in the weather that are due to these emissions, are becoming more and more obvious as time goes on. So we've seen some very unusual weather patterns in the last few years. The reason why this is a crisis for humankind and also for the environment is that strange weather or extreme climate change is a real stressor for both humans and also for plants and animals. It sort of pushes the envelope for the kinds of weather that we're used to, and also that plants and animals are used to and are acclimatized to. So the more we see this strange weather, the more we'll be stressing both vulnerable human societies, but also vulnerable ecosystems that may be at the kind of the margins of their ability to adjust to rapid changes in their surrounding climate. In terms of solutions, a lot of the work that we're doing here at the laboratory and also at the University of California in Berkeley is devoted not only to understanding the origin of the problem, but also in looking at a variety of really innovative solutions for generating energy in a truly sustainable way. And so Berkeley Laboratory has created a program called Carbon Cycle 2.0, which is designed basically to move on to a new realization of the world's carbon cycle, but one in which it's sustainable long term, and by long term I mean centuries to millennia. Berkeley now has a coordinated program launched in the last couple of years devoted to understanding and developing new ways of producing energy and on the large scale in a truly sustainable fashion. So the solutions involve transitioning our energy systems away from carbon-containing fuels to carbon-neutral or carbon-free fuels. And I'm happy to say that both Berkeley Lab and University of California, Berkeley are at the forefront of research in both in those promising areas.
Could you maybe talk a little bit about your own research into and your personal contributions in your work here to kind of that project you had here at Berkeley Laboratory?
So I'm afraid most of my research is devoted to characterizing the problem, basically understanding what will happen if we continue on business as usual. So if we were to continue emitting carbon dioxide, what the climate would look like in the future. The work in my department and my group here is devoted to really understanding how the carbon cycle and how we're perturbing it, how those changes to the carbon cycle interact with the rest of the physical climate system. And in some sense, we're sort of looking at a variety of forms of abrupt and extreme climate change that may come to pass this century if we don't alter our course of action. On the upside, the work that we're doing, we're building a new type of climate model in which the energy market and human beings are actually included as part of the model. And the idea now is to look at a coherent, integrated model to explore solutions. So with this new kind of model, we can project what would happen, for example, if we were to deploy carbon capture and sequestration on a large scale. How much environmental and climate change benefit would that have? If we were to deploy biofuels on a large scale, either cropped or more exotic types of biofuels, how much benefit would we see from that kind of deployment? So we're taking the climate model, which traditionally is sort of a crystal ball for all the bad things that could happen, and trying to turn it into a tool that will allow us to project the benefits from moving on to a more sustainable pathway. Looking at the combination of research in basic energy technology and also forecasting how those advances in energy technology will play out as we take them to market and begin to deploy them on a large scale. So again, building this crystal ball that allows us to look from the genesis of energy technologies in the laboratory to how they would play out in the market and at the state, local, national, international level, building that sort of that tool to really look out ahead and make sure that energies are deployed as best as possible. That'll be another major thrust for us going forward.